Welcome to lesson number 39 of the course on industrial automation and control. This is the penultimate lesson, and therefore, while we are ending the course, we need to be aware of at least some of the things that we have not done in detail. In this course, we have mainly talked about the lower levels of automation, namely level 0, where we have talked about sensors and actuators in some detail, and level 1, which is automatic control and sequence control. But as we have discussed, there are higher levels of automation systems. There is level 2, level 3, and conceivably level 4. So, in today's lesson we will try to take a look at it's going to be a brief look, but nevertheless take a look at what makes level 2, 3 and 4, so that we have some idea about them and get a more complete picture. This is about industrial automation, not so much about it turns out that the higher levels are more concerned with information technology and software rather than automation technology and hardware. So, therefore, they have not been treated in detail in this course. So, here we go. So, as usual, instructional objectives and name the higher layers. So, the student should be able to at least name the higher layers and name the major functions of each of the higher layers, level 2, 3 and 4 automation, and describe the many of them. There are basic technologies which are involved in this are monitoring technologies, optimization technologies. Part of it gets manifested in planning and scheduling. So, students should be able to talk about what is process monitoring, how it is done, why it is important. Then planning and scheduling, what is planning and scheduling, and how how in the overall automated factory industrial information technology plays a role in coordinating, integrating these complex operations for squeezing out performance, getting productivity, efficiency, to gain an edge of competitiveness in the market. Okay. So, we first take a look at the automation pyramid. Remember, we had taken a look at this automation pyramid in the very early parts of the course. So, here as we said that this is the automation is organized, it can be viewed as a pyramid with the process machine, the basic equipment at which is the ground, and then you have the sensors and actuators which take information and provide control inputs. Then you have the first layer of controls, automatic controls, and in this course we have mostly been concerned about these two layers. We will select thicker pen. So, we have mostly been concerned about these two layers, and in this lesson we will take a look at the higher 3 layers. So, all these layers are basically have different functionality, and obviously the higher layers take feedback from the lower layers, and they give reference commands or set points or to the lower layers as to what is to be achieved. They set the targets for the lower layers, and therefore, all this information. So, there is information passing back and forth. So, there is a communication system, and we have already learnt about such a industrial communication system. Then there is a spatial time scale difference among the layers. While the sensors and actuators look only at a part of a machine, but look at it in great time resolution. As you go up, the layers of automation at those levels look at much bigger geographical areas. First it talks about unit control, where one piece of equipment is looked at. Then you talk about group level control, where groups of equipment are looked at. Then you can talk about shop level control, you can talk about factory level control, and so on, and finally you can talk about enterprise level control. So as you go up, your geographical extent goes up, and your time resolution or your time scale also goes up, which means that you don't look at things on minute time scale, but start looking at things in terms of hours to days, days to weeks, sometimes months. So when you are doing enterprise level planning and optimization, you typically look at months of operation, while if you are looking at automatic control level, then you are typically looking at minutes level or signals at levels of second to minutes, right. So we see that this is the way complex automation systems are organized, and functionally, typically you will find that level 1 and 0 we have seen there. Levels 2, 1 and 0 actually basically constitute of control systems. So they talk about physical dynamics, they talk about the physics of the process, heat transfer, mass transfer, signal value. So they are kind of one kind of technologies. So they have been clubbed level 2, 1 and 0, they are all control technologies. Beyond that you have level 3, or sometimes the systems which, or the computing systems which support the performance here and do the kind of computation that are required, are called manufacturing execution systems which actually plan production, take a check at resources, track how particular how a particular order is being produced, take care of quality, etc. So such systems are the manufacturing execution systems. So they actually basically they are interfaces between the business and the engineering systems. So they take on one side the interface with the business systems and take orders, production deadlines, etc. And on the other hand, they actually produce, they take these targets from the business systems and they translate them into engineering targets, exactly in terms of schedules of production, which machine to be used at what time, and then and once these are now handed down to the supervisory control system, then the supervisory control system can act according to that schedule and actually execute the steps that are required to do the physical manufacturing, right. So functionally, you can have, if you see the nature of technologies, then you will find that this is one nature of technology which are essentially business systems, enterprise resource planning, etc. On the other hand, these systems are still related to the engineering equipment, but look at them as behaviorally, and just model them in terms of their functionality and their some performance parameters, and model the manufacturing process just like a sequence of operations while the actual physical entities are handled at the control system levels. So this is the way it goes. So we are going to talk about the supervisory control, manufacturing execution, and to some extent the business systems today. So if you take a brief look at the various levels. At the highest level you have enterprise level systems or business systems, where you talk about finances, human resources, you talk about documentation, you talk about long term capacity planning, whether you need to, looking at the order, looking at the market, whether you need to set up a new plant or you need to acquire a certain kind of machine, you what kind of production goals you want to achieve, and these are the kind of things that are actually done at the enterprise levels. And we are going to this is just for our awareness. We are not going to be we are not experts on this, and neither are we going to deal with this in a course, but it is good to know that this is what the business system does. It actually finds out, basically it is directly interfaced to the market, and it actually finds out that what should be the kind of production resources and production schedules, so that profit can be made. Below that is level 3. So, once this enterprise level comes out with orders and provides schedules of various, I mean the capacities which are going to be available, then the manufacturing level actually sits down and says, okay, so now I have to make so many pieces of this over such time with such kind of resources, right. So, now how am I going to actually do it? So, when am I going to make what, and how am I going to schedule my machines, and when I am going to maintain what, when I am going to take off a particular machine and then give it for maintenance. So, all this is done at the manufacturing level. So, typically you do a, so once you have done that, then you know the exact production sequence and when what will be produced. So, you have a kind of schedule. Now, you can send this schedule that, okay, now everything is fixed up. So, now you produce, actually physically produce according to this schedule. So, then the supervision level actually takes this and makes the, firstly it makes the production, that is it actually finds out the configurations of these machines as they have to be configured for a particular manufacturing, and they actually run these machines according to this, download the configurations and then give the proper commands, such that the machines actually start producing. And they also supervise the overall production process. They actually optimize and deploy control strategies. So, they actually manage the whole production. Sometimes it is done automatically, sometimes it is done manually. So, when it is done, so so in many cases it is done manually, that is using operators. So, these systems visualize, give the operator a view of what is happening in the plant. They also store process data for future use. They do a lot of documentation which can be used later on for quality tracking purposes, for process improvement purposes. They actually command several units in a very coordinated fashion, such that best volume and quality of production can be reached. So, they coordinate individual groups of machines and they give them appropriate set points, so that you get products of a certain quality and of a certain volume. And they also handle plant emergencies, shutdowns, failures, accidents, etc. So, they actually manage the production process. Below that you have the actual automatic control, in this case referred to as unit control, and below that you have the field level where you do sensing and data acquisition. Since we have done this in detail, I am not going to spend time on this. So, this is a picture which shows that typically in a process control situation, not a discrete manufacturing scenario, the kinds of technologies that are used. So, you have and also the time scales that I was talking about. So, you have at the bottom level you have these sensing, actuation, protection, alarm systems, which typically work at sub 1 seconds kind of time scales. Then you have the what they call regulatory control, or which we call automatic control. So, this is kind of level 0. Then some of it is actually level 1, and then this, as we said, that you need to give very good set points to these automatic PID loops. So, that is again computed by multivariable control models, where you consider the interaction among the various variables. You do what is known as model predictive control. Is a very modern technology which is used for using number of process plants. So, here you are talking about giving set points which hold for typically for over minutes, hours kind of horizons, and then you have real time optimizations, where real time optimization is also done at the level of multivariable and constraint control. So, you have real time optimizations for actually for various kinds of, excuse me, I have to switch off my mobile phone. The interruption. So, and then finally on top of that you have the planning and scheduling modules, which again, as I said, that decides what is to be made and typically work on days, months, weeks kind of time frames. So, this is a diagram which shows the various kinds of technologies that are used. For example, for planning scheduling, you have to do demand forecasting, you have to do supply chain, you have to, if you want to know that what sort of what should be a schedule, then you have to know what kind of orders are going to come, what is your inventory, what time does it take to actually procure raw material from the market. So, that is supply chain management, raw materials and product planning and scheduling. So, at these various stages you use different kinds of techniques, and there are very advanced software tools today available which actually help plant managers take these decisions. So, so we come to So, now we start talking about the various levels, and we start with from level 2. So, level 2 is supervisory control. So, the major functions of supervisory control are the following. So, you have first of all optimal set point computation. So, when you are supervisory control is typically concerned about a group, one machine or a group of machines, and they have to be their operations will have to be coordinated. So, you have to give them optimal set points, so that they can achieve the performance goals of the production. Like typically, let us say a supervision system will, let us say they if you take a steel plant, then you have a blast furnace feeding to the steel melting shop or the basic oxygen furnace, and then basic oxygen furnace feeding to the continuous caster. So, you need to give set points to all of these. For example, the continuous caster will have a set point given to it of the casting speed, that is at the speed at which the slab is going to come out of the caster. Now, obviously, that is going to be decided based on the kind of molten steel supply situation, right. So, the molten steel supply situation depends on the basic oxygen furnace. So, you see that these set points, firstly the continuous caster casting speed specification has to be given based on some, there are some other considerations also, like for example, that there is a phenomenon called breakout, where if you do not give the proper cooling set point, cooling system control and the proper casting speed, then sometimes molten metal can actually come out of the slab, and then you have to stop production, and there is a lot of problems, right. So, there are other technical considerations, but there are also considerations related to coordination among the different units. So, all this is done by the supervisory control layer. Similarly, one has to supervisory control always looks at the process and sees whether things are going fine. For example, breakout detection, as I was saying, that whether by looking at the temperature profile, by looking at the mold levels, whether it is possible to, the system is always monitored such that whether we can detect the possibility of a breakout and then immediately take corrective action so that breakout does not occur. So, that would be like process monitoring. Similarly, if process reconfiguration and tuning, sometimes it happens that you need to retune your controllers because the process slowly changes, or because there may be some problems with the raw material quality, or there may be some problem with some power source, like let us say the pressure source may have a low pressure problem. So, in such cases sometimes you may have to retune your controller such that it gives optimal performance in terms of quality, efficiency, energy efficiency, etc. So, the direct result of monitoring is reconfiguration and tuning as and when necessary. Similarly, sometimes this is done, all this is done manually. So, if it is to be done by operators, then the operator has to be given a very good insight about the things that are happening in the plant, which may be quite far away from the control room. So, there is a process visualization system, man machine interfaces which have to be provided. And similarly, process event management. So, I mean something trips, some alarm goes, some pressure level shoots up. One has to activate strategies, shutdown mechanisms, emergency mechanisms, such that the situation is managed with the least amount of production loss, with safety and reliability to the personnel and the equipment. So, such things are typically handled at level 2, or these are the functions of the supervisory control. So, essentially when you are giving a set point, there is an element of optimization involved in this. So, that is shown here, that this is your automatic control loop. So, this is your automatic control system, this is your set point, this is the set point, and this is your system, closed loop system. So, you always try to find out that. So, first of all you get the data from the process and you actually reconciliate it, that is they may contain noise, some sensor may be they may be inconsistent because of various reasons. So, first you, before taking decisions, you reconciliate the data that all the signals make sense according to standard mass balance, energy balance equations of the process. So, once you do that, then you have got good data, good and valid data. Now, based on that you may like to compute various kinds of performance indicators of the process. What is the production volume, what is the deviation from quality, what is the for example say what is the magnitude of the control input, that what is the input energy that have been consumed, what is the agility of the plant, what is the dynamics, that if there is a set point change, what is the process variability. So, various things, various features of process operation can be computed, and based on that you get an idea as to whether your process is working fine, or whether it needs a new set of new set points, that is another cycle of real time optimization will have to be done to generate new set points. So, this is typically the way in which the supervisory system is always looking at the plant and then carrying out optimizations based on set points. Now, these optimizations can be done in various ways, and finally you want to minimize cost of production, and cost of production generally per unit, and you as we have talked about in our first beginning slide, that if you want to make more profit, then I have to cut down on the cost and I have to increase the production. Now, increasing production how far? So, that can be limited by typically by two kinds of things. Firstly, there are quality constraints. You cannot produce things too fast, because then they are going to, they may not be of adequate quality. Then there may be production volume constraints, that you cannot, you do not now how much, even if you can meet the quality constraint, how much you can produce can actually depend on your equipment capacity, how many it can actually produce, or it can be restricted by the market, because you do not want to produce things which will not sell, right. So, so typically if you go to a I mean, this is what I always find, that if you go to a sweetmeat shop or some food shop around 9 o'clock in the evening, you will find that many of the items have been finished. So, they actually schedule their production in such a manner that towards the end of the day it gets exhausted. So, I mean, they will not produce more, because food is a perishable item, and they don't want to produce more than they can sell. So, sometimes volume of production can be also constrained by the market. Similarly, where you have very energy intensive processes, or where energy is the main bottleneck, like in a let's say an aluminum refining plant. Say an aluminum refining plant actually works on electrolytic principles, and it is highly energy guzzling, and it works on electric energy. So, it's that way a very clean plant, where literally hundreds of thousands of amperes actually flow through those aluminum pots. And these here I mean, in such a plant, production is can sometimes be actually limited by energy, because it may be because that amount of electrical energy, some of it typically aluminum plants have their captive generations, but sometimes they may also draw power from the grid, and in which case especially in developing countries like ours, there may be constraints on that. So, in such a case energy consumption will be a very critical optimization criterion for giving set points. So, similarly, minimizing waste through effluents. So, that can be, again it can be, for example, you typically optimize fuel air ratio to save calorific value of unburnt hydrocarbon. You do not want carbon monoxide to actually escape into the atmosphere, because that can be burnt further, and you are actually, if you are escaping carbon monoxide, then you are actually losing calorific value of the fuel that you are using. That is number one. Number two is that sometimes you may be restricted by environmental considerations, like you cannot dump acidic or basic effluents into rivers, right. So, there can be, what I am trying to say is that in a typically in an industrial scenario, you can have various kinds of optimization criterion. Second thing is, the second thing which is important for a production is that process variability. That is, typically you want to maintain a certain set point you are holding, but still the process signals or the process final product parameters, let us say a steel strip thickness coming out of a rolling mill, you have the same roll gap. So, you want that a steel bar comes of a certain width, and when it gets rolled, it should come out with a certain level of thickness, right. So, you have accordingly you have set your roll gap, right. So, this gap is gap between the two rolls you have set. So, your set point is fixed, but it turns out that there can be enormous variations in, I mean, there can be quite a bit variations in roll gaps depending on other factors. For example, the temperature of the bar which is entering. So, if the bar is heated to the appropriate temperature, it will get rolled easily. If the bar is not heated, if the bar has cooled down little bit because it was waiting to be rolled for some time, so its temperature has fallen down, then it will become considerably harder to roll, and therefore, the dimension reduction may not be appropriate, right. So, such things can give a lot of process variability, and once you have a good, see, you want for the product to sell, you need a certain quality finally. So, in the case of sometimes if you are storing in tanks, as we have said that as you are storing in tanks and if you have widely fluctuating product quality, then you actually need a large tank such that all these variations when they actually come to the tank and finally gets mixed, then they come to an average quality. So, if you may have a small tank, then obviously integration over smaller time of a sinusoid will still give variations. So, if you want to reduce variations, you will need to have large tanks. On the other hand, in the case of discrete manufacturing, you are not each piece is actually different. So, it is not that if you manufacture more length of steel plates, then you can tolerate certain kind of variations. I mean, variations on one part will not cancel the other. So, in such a case, you have to for example, suppose a railway wheel, it has to have a certain amount of weight. Now, now when you are cutting an ingot, you are first cutting an ingot and then shaping the ingot in the form of a wheel. Now, when you are cutting the ingot, if you cannot cut precise amounts of material, then what is going to happen is that you will always play safe, because you do not, if it becomes of less volume or weight, then it will be totally rejected. So, you will try to play safe and you will actually set your limit higher. So, you will cut more material, then finally that additional material will have to be machined, and you are not only going to waste material again, but you are going to waste machine time. So, if you have high variability, generally you do not have good performance of processes. And variability, big variability generally comes for various kinds of problems in processes, like common problems which occur, like for sensors they may have there may be improper calibration. Improper calibration will directly result in dimensional inaccuracy. If you have noise, then because of noise feedback, things will there will be perturbations in the output. Similarly, thermo wells, when they get clogged, they actually can insert quite a bit of time constant, and therefore, especially when you have shifting set points, then the process will not track the set point well, as we have learnt. Similarly, plugged lines can give, plugged lines means all these sensors will actually sense. So, maybe you are sensing a pressure sensor, and you have a line which actually connects the process to the meter and senses the pressure. Now, this line, if it is plugged, then the pressure will not be properly sensed and the sensor will give bad readings. And sensor readings, as we have seen earlier, that sensor readings, sensor errors in control systems directly affect the output. So, if you have any problem in the sensor, it is going to be directly transferred to your output. Similarly, you could have actuator problems, various kinds of problems like friction due to lack of lubrications. Then actuators also have sensors, so there may be problems there. There may be problems of electronics or problems of sealing. Sometimes fluids will leak, say hydraulic systems, or problems of power sources. For example, suppose you have a pneumatic actuator, and if you have less air pressure, or you have a hydraulic actuator and your hydraulic pump pressure has fallen. So, such problems give problems in the actuator. These are very typical problems. Similarly, controller may be badly tuned, right? And similar, and of course, the process can develop leaks. It can develop scales on heat transfer equipment. Things can get clogged. So, all these kinds of problems can occur, and these problems generally make the performance of the control loop inferior. So, one needs to all the time check whether the control system is actually performing adequately. So, that is the basic job of process monitoring. So, you have process monitoring. So, the basic job of process, there are you can divide process monitoring into two ways. One is performance monitoring, and the other one is failure detection or diagnosis. So, when you are doing performance monitoring, then you are ensuring that process variables are within specified limits. So, you are So, no limits are being crossed, quality will be okay, and you are also ensuring that other key performance indicators, for example, energy being spent or compositions of waste compositions etc., or so scrap, the amount of scrap or the amount of raw material that you are consuming per unit product. This could be key performance indicators, or the loop dynamic performance, these are within limits. So, while you are doing performance monitoring, you are trying to look for better optimization opportunities, but as such the plant is operating okay. Contrasted to that, you have situations where something goes wrong, something breaks. So, there are abnormal process operations, and then you have to diagnose the root cause early enough for correction. So, that it can be corrected and the operation does not get jeopardized. So, these are the two kinds of functionality, main functionality for process monitoring. Process variability checking, this is a standard control chart. So, you take lots and then you from those lots you actually calculate mean values, and then you plot the mean values and you continuously try to see. So, you have decided some upper control limit and some lower control limit, and you try to see whether the mean values are actually contained within that. In some cases they may go out. If they go out, that is cause for concern. If they go out too often, then they are cause for concern, and you need and you know that your process variability has increased, right. So, the process is not being able to follow a particular kind of output properties, but the output properties are varying and there is a lot of variability. So, which means that something has gone wrong, right. So, you need typically you check process variability using such charts. Often process monitoring, why we are showing this diagram is that in many cases process monitoring is actually done by expert operators. So, there is always a question of having man machine interfaces, and there are lots of issues in their designs, like for example, previously older this is a typically it looks like a power plant, power substation. This is a power, here is the bus, here is the bus, here are the various feeders. This is a probably some sort of machine. So, you have these are various meters, then you have relays at the back and things like that. So, you see that these are a panel, these are called control panels or mimic panels sometimes. So, previously what we used to have such mainly such man machine interfaces where so you have big meters, and they are. So, now the design of these have to be such that it is easily problems. See, an operator looks at hundreds of these meters, so they have to be properly color coded, so that an operator can from a distance he can quickly make out what is the source of the problem. Their placements, more important things should be right in front of the operator. Then the various controls should be such that the operator can very closely operate it. So, you have various kinds of joysticks and other controls where the operator can conveniently give manual control commands. Of course, graphics, audio visual clues, alarm annunciations. So, some lights glowing, some hooters, and proper labeling, that is each variable should be properly labeled, so that the operator can quickly make out the situation. So, there is a lot of these are called human factor engineering, sometimes referred to as ergonomics. So, there are lot of such thoughts go into the design of such man machine interfaces. On the other hand, if you see some modern interfaces, many of it will be for example, you can see here that apart from these, the operators will have computers. So, there will be VDU or CRT based displays, which will also show these are the modern kinds of man machine interfaces. Typically, a man machine interface shows to the operator these three things. It shows the current state of the process, it shows alarms and events, and it lets the operator compare performance against trends and history. So, these are the three kinds of information that a man machine interface, a modern man machine interface based on computers, makes available to the operator. So, these are the major functions of man machine interfaces: data acquisition and display, then measure and processing. It calculates the various derived values, that is, it does not always produce raw data to the operator, because that the raw data does not is sometimes requires further processing to give more meaningful operation information to the operator for effective plant operation and management. So, such measurement processing will go on. And so, measure and processing, then events and alarms, it will clearly show the events and alarms, their sequences, then etc. So, how the things are happening, when which signal has reached some high or low level. So, all these things, all the sequence of events that are happening in the system, it lets the operator see it. It maintains a history database and generate logs and reports. It also takes the operator commands and applies it to the plant, and finally, it integrates with the higher layers of automation, like for example, in this case which will be a which may be a manufacturing execution system. So, these are the main functions of. Now, it turns out that as you have seen from the previous picture, that there are hundreds and sometimes maybe close to 1,000 variables and loops that that an operator may be required to monitor. So, there is a need for it is very difficult, and there is a need for automated monitoring, and therefore, purely manual monitoring requires lots and lots of experience, and even then operator errors are cannot be ruled out and have occurred in various situations, just like they occur in aircraft accidents. Aircraft accidents also, the pilot has to see a whole lot of signals and take very time critical decisions. So, the control performance monitoring, automated control performance monitoring actually basically tries to determine whether the control system is performing satisfactorily. If not, then to diagnose causes of unsatisfactory performance, and then finally, it generates action which could be retuning of controllers, or it could be activating special shutdown or emergency procedures. So, this is the basic idea of performance monitoring. Now, if you want to monitor, if you want to basically determine whether something is going wrong, then just a moment. Okay. Machine interface, then so we have seen this one. So, what I was saying is that if you want to find out whether a plant is working perfectly, then you need to do two things. Firstly, you need to check with a benchmark, something whether it is good enough. So, first of all you have to determine, so you have to first of all look at some quantity. So, what are the quantities that you are going to look at to understand whether the plant is performing properly. So, you need to select some response parameters or some performance indicator, and then you need to check whether its value is okay. So, you need to define what is okay and what is good enough. So, that is called a benchmark. So, what you do is So, you could have various kinds of benchmark. For example, you could have response parameters like rise time, settling time, overshoots, offsets, integral error criteria. So, all these could serve as benchmarks. So, if you have a too high an overshoot, then you know that there is something wrong, and one of the reasons could be that the loop delay has increased for some reason. Maybe the sensor thermo well has accumulated some material. So, the sensor lag has increased, and therefore, you are getting too much overshoot because the overall loop phase has increased, right. Similarly, you could calculate some certain signals, and we will see what this in little more detail. You can, if you have a model of the process, I mean a dynamic model which could be described in various mathematical terms, then you could generate a residual, that is you can generate a signal that as long as the system and the model are close enough, then that signal is going to be small. If the system deviates from the model, then the signal will grow up, and then you can try to look at that model, you can try to look at that residual, or you can look at, you can even look at historical data, you can look at historical data saying that, and which you know that this is satisfactory performance. So, you can always compare. So, suppose some maintenance was done in the plant, and immediately after that you know that the plant was working fine. So, if you have the historical operational data stored with that, you can always compare with that, and then that can also serve as a benchmark, right. So, there are various ways that this process monitoring can be done. You can try to monitor various things like production volume, production quality. For example, you can strip quality tracking in rolling mills, or ladle tracking for continuous casting, because so that you know that you can achieve a certain amount of number of heats in a continuous caster. This was actually a problem for our steel industry, that they were not having enough number of heats. Similarly, you can have equipment health or performance characteristics, like you can actually monitor machine tools whether they have got worn out. You can have fire brick linings, check fire brick linings of furnaces. Similarly, you can monitor process operations, like detect when you are pouring metal, when slag is going to come or not, and etc. etc. So, you can monitor various kinds of quantities. So, as I said that how to monitor a process, you compare a process signal or some other signal derived from them with their expected or normal patterns. So, expected or normal pattern you have to calculate. Then how to obtain expected or normal patterns, either by checking threshold high and low limits, which you have already set, or by checking material and energy balance errors. So, for example, if you know that the mass of material which is going out is so the mass of fluid which is going in and the mass of fluid which is going out are not matching, then there could be a leak in the equipment. You can check certain parameters like heat transfer coefficients. If a tube develops scales, then the heat transfer coefficient is going to fall. Or you can also sometimes check sensor failures by physical redundancy. You have more number of sensors, so you check whether their readings are tallying. So you know that if one of them is not tallying, then you know that sensor is faulty. So, you can have several such ways of monitoring the process signals. So, you continuously look at the process signals which you are acquiring, and then using various kinds of physical models or various kinds of experimental models which are mathematical models. You can do computation which can tell you whether the behavior of the process is as expected in terms of performance. So, I will skip this little bit. This says that the residual signal, model based residual, should be calculated such that when there is no fault, then the residual is going to be very small. The moment there will be a failure, this residual will grow up, and so looking at the residual you can determine whether there is a failure in the plant. So, residuals can be generated by various ways, various kinds of signal processing algorithms. We do not have time to discuss those. We will skip this, and before I leave this level 2, so we were discussing level 2, and I would like to say that all these both the optimization of set points as well as process monitoring require a lot of knowledge. So, you have to have good process databases, and you also have a good knowledge base, so that you can actually perform these computations. So, this operation and process databases are very important components of supervisory control. Now, we come to level 3 automation. Basic functions are material and production tracking. So, how the production is actually taking place with respect to a certain order, material handling and production procedures, how the material will actually move from one machine to another machine, what will be the sequence, first milling, then turning, then boring, or what. So, the actual production procedures, then resource management and allocation, how many machines you have, how many you are going to allocate to what batches and what orders, production dispatching. So, finally, when you have determined them, then finally dispatching these to the lower level for actual production, data collection and quality assurance. So, assure that from the data that you have got from the supervisory control level, as well as from the quality shop, ensure that you are meeting quality standards which are required. And finally, overall performance analysis, the plant audits in terms of material consumption, energy consumption, costs per unit cost, etc. So, all these are typically done at the manufacturing automation levels. Document management is a very important part of modern standards. So, for all these things, for all this doing all this, you have manufacturing execution systems, which are computer systems which let you do all that. So, basically this is exactly what is being said, that the manufacturing automation system, this I also said earlier, that the manufacturing automation system actually sits between the business system and the shop floor automation. So, it takes the business system requirements and targets, and then in turn generates the targets which can be then sent over to the shop floor automation system, which is going to actually meet those targets in terms of volume and quality and efficiency of production. And that process is actually basically short term planning and scheduling. So, in short term planning is something which you do in the business system, typically that is in level 4, and so you make choices with respect to order acceptance, capacity planning, delivery times at sites, etc. And then you take these short term plans, and then you further augment them with actual production sequences, production times, route through the machines, etc. And then you also elaborate them kind of week by week, day by day, so that you have a much more detailed schedule. So, these are the differences between basically scheduling is also planning, but over a longer horizon and with respect to the equipment which you are going to deploy. So, typically this is production scheduling. So, you determine you want to determine production amounts, that means lots and batch sizes, and you are given the planning horizon and the demands and the inventories. So, how much is going to be required, how much you can store, over what time you should plan. If you are given these, then you plan the lot and batch sizes. You can plan timings of operations, the run lengths, that is each set of batches, how you are going to run them, and that you can actually determine if you know the precedence order in which the machining has to be done and the resource utilization. So, similarly you can determine how you are going to at which sites you are going to produce these, using which units, which equipment items, etc. Okay. So, this is what you essentially do in production scheduling. Now, if you take finally we are going to take we have to take when we go to higher and higher, then we have to take an integrated view of the business, and that is sometimes modeled as a supply chain. So, you have on the one hand we have the orders, and based on the orders you have to do resource planning, and you have to actually make your raw material logistics, that is how you are going to procure the materials that you are going to transform to finished products. Similarly, you have to have you have to create the facility for production, which can come from R&D, basic engineering, and then construction. So, you have to do capacity planning, you have to do actually manufacturing resources you have to put together. So, once you bring the raw material and the manufacturing resources, then you can actually do production. Here you can do production. So, this is the place where you do production, and then once you have the production, then you have to finally it has to start with the order and it has to end with the delivery, right. And all these DCS supervisory control actually work in only in this part. There is these parts are still managed by the enterprise or the business systems which take the product and finally ensure that the order to delivery sequence actually takes place. So, this is, and obviously if you want to manage the whole supply chain, then it requires actually basic coordination between these systems, which are sometimes called business systems, and these are the MES and the DCS, manufacturing execution systems, and the distribution control systems, distributed control systems, and these are the B2B systems. So, these systems obviously require synchronized business and manufacturing systems. So, this is the essence of it, that they have to be synchronized and they have to be integrated for ultimate coordination, right. So, that is why you need to, so all these, so as we have told, we don't need to elaborate this, that so the enterprise level system typically decides on the business parts, long term planning, finance, human resource, and sets production goals, capacity plans, etc. And this, so basically they are also trying to do optimization, they are also trying to do planning, and so if you, so at that level you do what is known as enterprise resource planning. So and then these enterprise resource plans have to be finally taken up by the manufacturing execution plan, and then actually they have to optimize them so that you get the response. So, the ERP system actually says that what kind of response is desired, and the manufacturing execution system creates plans for lower level systems such that such response can be generated, right. So, they need to be obviously be very integrated, and this integration can actually be in both directions, that is there can be vertical integration right from the enterprise systems down to the automatic supervisory control, automatic control. So, that is vertical integration down to the machine that actually produces it, and they also require horizontal integration in the sense that you need to integrate your activities over different sites, between warehouses, factories, right. So, that is special integration, or that is called horizontal integration. So, you need integration on both sides. We will skip these because we are running out of time. So, finally, I would like to just comment that for making all that happen, you need actually a lot of intelligent automation, and therefore, you need a lot of deployment of industrial technologies. Finally, lesson review. So, in this lesson we have talked about in brief we have tried to scan the 3 levels, level 2, level 3 and level 4 automation, and finally, you have some points to ponder. You can describe the levels of functional hierarchy, name 3 major functions, basically describe how to generate residuals, etc. So, that is all for today. Thank you very much.